Yes, good morning, dear students. Today we will discuss searching algorithms. I hope my screen is visible to all of you, right? Yeah. So, in searching algorithm, today we'll discuss linear and binary search. Okay. Right. For example, you have an array of elements. Okay, like 10, 5, 50, 25, 20, and let us say 12. Okay. You want to search for a key, which is let us say 25. So in linear search, how do you search this particular key in the given array? This is your given array elements. This one dimensional array. Okay, consisting of about how many elements? 6 elements. Starting with the index 0, 1, 2, 3, 4, and 5. Okay. Now, in linear search, what do you do is you will take this key and compare the first element of an array. This is your first element. How do you access the first element with the indexing mechanism, right? All the array elements are being accessed with the help of indexing mechanism. So here you are going to compare a of 0 with key. Okay, that is 20, and your key is 25, right? Are they equal? No. Then what will you do? You will compare it with a of 1. Like that, you will compare all the elements of your array until you find your key, right? Okay, so where can you find this element? Here, a of 3. So at a of 3, you will get the element, right? So you will be comparing your key starting with the first element of an array until we could able to find. Say for example, if you could able to find somewhere here at the index 3, then you will have to stop further searchings rather, right? Further comparison you have to make rather, right? And you can say the index position at 3, you could able to find this particular key. This is what the logic is, right? This is the successful search, right? So basically, you will find two, cases. One is successful. Another one is unsuccessful, right? When you can be able to find, you say it is a successful case. For example, the key which you are trying to search is available in the array, so it comes under the successful search. So fine, you could able to find. Then another case is unsuccessful. So for example, you are searching for, let us say, 30, okay, which is not available at all in this particular array. So what will you do? You start comparing it from the first element of this particular array, starting with the index value 0. You will compare your key with a of 0. If you cannot find, you will further move and then compare a of 1 with the key. You will be comparing your key with all the elements. Here you can see the array size is about 6. So the index value starts from 0 till up to 5. Then once you could able to compare the last element, that is at the index of 5, after that you don't have any element rather, right? So if you cannot able to find, let us say, this 30, you cannot able to get this particular condition being satisfied, okay, until the last element, then what will you say? You say key not found, right? Key not found. This comes under the unsuccessful search, okay? This comes under the unsuccessful search, right? So now you have to devise an algorithm for the same. So here I am writing the algorithm for the same. Linear search. Okay. We start with begin. Then what are the variables you require? You require an array here, integer array you are taking of, let us say, some size. For example, let us say 6 or whatever it could be. And you need a variable I, so you are taking that variable I here. Okay. Okay. And then you need a key to be searched in this given array. So these are the, you know, variables required. I'm taking another variable called flag actually, which helps me to identify whether the element is found or not. So initially I'm taking this flag value as 0. Okay, so let us say these are the variables to implement this particular algorithm I'm taking. So here, what is the input? Array and your key, right? So you will read them, read key and array, right? Read array and key, okay? We will read both of them. Then your logic starts, right? So here, how many elements you have? 6 elements. So you need to take a for loop here. So your array index starts with 0 till up to last one. So I plus plus. Okay. Inside this for loop, right? You will be comparing your key with all such elements of the array, right? Whether key is equal to a of I or not. So if key is equal to a of I, you will be changing the flag value. Okay, you will be changing the flag value to 1, and you will and then you will break, because you don't need further searches, right? Once you find the element, you don't need further searches, so you'll be breaking the loop, right? And then when you come out of the loop, rather, right? When you come out of the loop, you will be comparing the flag value. See, I'll be terminating this for loop here. Inside the for loop, what is the logic we have is nothing but we are comparing key with a of I. Okay. It means starting with I value 0, it compares with a of 0 first. If it is available, then immediately change the flag value, and then further searchings will not be done because you have a break, and so you come out of the loop. But if, let us say, the condition is false, it means key is not available at the first position, that is at the index value 0, then it goes for the next iteration. By taking I value 1, it comes back for next comparison. Like this, it does. How long it does? Until the last element. So the last element index is 5, right? So even if, say, for example, at the last element, that is with the index value 5, key could not be found, it means this condition is false for all the times. Then what happens? Then, this condition will be false for all the times. So you will be comparing all the elements, and then when I value becomes 6, you will come out of this loop, right? So that is your unsuccessful search, right? So in that scenario, flag value will be 0 only, rather, right? Because you have started with 0, and then you are making a comparison here. If the condition is true, flag is going to be changed. But if the condition is never true for the entire iteration, then probably the flag value will be 0 itself. So when you come out of the loop, based on the flag value, you are going to decide whether the element is found or not. If flag value is 0, it means key not found. If flag value is 1, it means when the condition is true inside the loop. When the condition is going to be true, when the key is found at any position of the particular array, rather, right? So when the key is found, then you are changing the flag value and coming out of it, and then saying that the key is found. So here flag, if let us say equal to 1, what's that you are saying? Printf key found, right? Key found. This is algorithm, so I'm not bother about the syntax. Then else, what do you say? Key not found, right? Okay. I hope you understand the program. Now end the algorithm here. So in this algorithm, this is linear search algorithm here. So you can see you are taking one array of 6 size and key flag another variable you have taken which is initialized to 0 first. You have read the array and key here. Then here you are comparing key with all the elements of an array, right? Starting with the index value 0. So if at any point of time key is found across the array elements, then this condition will be true and flag value will be changed. When you come out of it, because you have a break statement to break the loop, because when you found the element, you need not to do the further searches rather, right? So you come out of it and then say, since the flag is 1, key is found rather, right? But if let us say for unsuccessful search, because we have to design the algorithm for both the cases, as we have discussed before, right? There will be two cases, successful and unsuccessful search, right? So in unsuccessful, what happens? You need to compare all the elements with, you know, but then you are not able to find your key across any of the position of your array, right? So it means this condition will be false for the entire duration of the iterations of this particular for loop. So when you come out of the loop, you find that flag value will be 0. It means this condition will be false and you come here and you say key is not found, right? So this is how the algorithm is. Now we can write the program for the same. I hope the algorithm is clear to all of you. Yeah, I'm going to online GDB. This is an online compiler here, which I'm using to demonstrate this program. So I'm writing here the program. Can you see my screen? Is it visible? I'll be increasing the size of the font here, large size, I've made it. Okay. Now I'm writing the program for the same year. So what are the variables that I need here? I need one array. I'm taking one array, int a of let us say 6. You can change also, as I said, if you want to have desired size, then probably you can take a variable with which you can rather restrict from using keyboard. Then I need a variable I need a variable key, then I need a variable flag which is equivalent to 0 first. Okay. Now I have to read the array and as well the key, right? So let me first read the array. I'm saying enter the array of 5 elements. Or you can see here, I have taken 6, so I can say 6 here. Now, to read an array, we need a for loop rather, right? I equal to 0, I less than 6, I plus plus, right? So I'm reading here the array using scanf, right? Percentage D ampersand A of I, right? Ampersand A of I semicolon. Here I need to say scanf, right? So scanf. And now I have to read the key as well, right? So enter the key. To be searched. Okay. Then I am reading the key with the help of scanf statement. Okay, from the user. So since it is integer, I have to give percentage d inside the double quote. Then I should say ampersand key after the double quote comma, right? So now I have read the key here. I've read the array and key. Now the next step of the algorithm. What is the next step of the algorithm? After reading the key and array, you'll be having this logic. This is what your logic is, right? You have to compare your key with all the elements of the array. Wherever you find, you will be changing the flag value and then breaking the loop. Otherwise, you will be continuing how long until the entire array is being compared. When you come out of the loop, you will be comparing the flag value. If it is found to be 1, then you say it is found, otherwise not found, right? So this is the logic which I am going to write here. So for I equal to 0, I less than 6, I plus plus. So here I'm saying if key is equal to A of I, okay, then you are changing the flag value to 1 and say break. Okay. And then when you come out of the loop, you will have to check the flag value. If the flag value equal to 1, only then you say key found, right? So printf key is found at which position? Key found at percentage d position, comma, say I, okay? I is the index at which it was being made available, right? Else you will say key not found, right? So printf key not found, key not found. Okay, so this is the algorithm. Okay, the same algorithm I've transformed it into the program, C program. I hope this is clear to all of you. Now I have to run this program here. Select the language as C here. Okay, then you can run the yes, now you can run the program here. Can you see here? The console where you are asked to enter the array of 6 elements there. Yes, I have to enter the elements. Let us enter 10, 5, 12, 25, 15, okay, and 24. 6 elements I have entered. Yes. Now it is asking us to enter the key. Let us say I am entering 25 to be searched. Okay. Now let us look at key found at third position. Yes or no? It is available at 0, 1, 2, 3. Third position. Yes or no? So key found, which means it is working for the successful search. And similarly, you want to execute and see whether it is working for unsuccessful search or not. So again, you are asked to enter 6 elements. Let us say you have entered 6 elements here. Okay. Now, I am giving a key value which is not available in the array elements, right? 35. 35, is it there? No. So, key not found, right? So, to decide whether key is available or not, it had to search all the elements of the array. Only then it can take a decision. So here you can see all the elements of the array are going to be compared with key, and if none of the array element is being matched with the key, then when you come out of the loop, the flag value will be retained with 0, and since it is retained with 0, this condition false, it goes to the else, and then it is going to print key not found. Okay, I hope this is clear to all of you. Yes. Yeah. So now we'll see another algorithm here. We'll see the binary search. You can see in linear search, there are two cases we found, right? Successful and unsuccessful. So in successful search, again, you can find there are three cases. If the element is found at the first position itself, you have to make only one comparison, because once immediately it is found, you are breaking. It means you are not doing the further comparisons rather, right? So you are risking from doing the rest of the comparisons. That's why if you can see the complexity of best case is going to be 1. And what are the other cases that you may find in successful? It could be an average case. Somewhere if you find the element nearby middle of your array, right? So n by 2 comparisons you require to make if provided n elements in the array rather, right? And the worst case scenario, that is the element is found at the last position. You have to make all the comparisons. That is going to be n, right? There's a worst case scenario. So you will find three cases under successful: best case, average case, and worst case. Whereas under unsuccessful, only one case, that is worst case, because you have to compare all the elements. Only then you can decide whether the element is not available, rather, right? So here I'm just discussing the time complexity of all these different cases that are coming under the successful and unsuccessful of linear search, right? And complexity means the amount of time that it takes to execute for such kind of inputs, right? So as I've said, there is one successful case you have, another one is unsuccessful. But best case, what is the time complexity? Is only one, right? Constant, because you could be able to find the element at the first comparison itself. In average case, somewhere nearby half of the array, right? And worst case is after the entire searches you have made, at the last position you could find. So in that case also you have to perform n comparison. But under unsuccessful you will find only worst case scenario, that is big O of n, right? So if you look at linear search time complexity, the disadvantage associated with this particular linear search is in order to justify that the element is not available, in order to identify that the element is not available, you need to make how many comparisons? N comparisons, right? You say, for example, the array consists of about 1 million elements, right? Then how many comparisons you have to make in order to decide that it is not available? You have to make 1 million comparisons, right? Yes or no? So 1 million means around 10 power 6, right? Is equivalent to 2 power 20 almost, right? 2 power 20. But then what we are trying to do, this particular complexity, we are trying to reduce it with the help of this binary search, right? So in binary search, the precondition is the elements are required to be sorted before, right? What is the precondition here? Elements are required to be sorted first, right? So under sorting, we have selection sort and bubble sort. We'll see probably in further classes, right? So here, the elements are required to be sorted in the sense that either it has to be put in ascending or descending order. We can take ascending order. So for example, like the elements are like this, right? Okay, then only the binary search is being not possible. But if you look at the time complexity wise, the algorithm, which we are using, which helps us to reduce this time complexity to logarithmic, okay, log n. The worst case time complexity is log n, right? So log n means here n equal to, let us say for example 1 million, which is equal to 2 power 20, then it's going to be log of 2 power 20 to the base 2 is going to be 20 of log 2 to base 2, which is nothing but 20 itself, right? So within the maximum of 20 comparisons, you can be able to decide whether the element is available or not. As against to linear search, where in order to identify the element is not available, you need to make how many comparisons? 1 million comparisons. For the same 1 million elements, only 20 comparisons will help us to decide the element is not available using binary search. So this is the advantage of going for this binary search algorithm. Now we'll look at the algorithm, binary search algorithm, right? So in binary search algorithm, what we will do is we will take the middle element, right? We will take the middle element. For example, you have these many elements, let us say, okay? This is your array. Array consists of about 5 elements, let us say 0, 1, 2, 3, 4. Okay? Now, let us say you want to search 30. Want to search 30. This is the best case in this particular scenario. So what you will do is you will find the middle element. See, this is the lower bound of your array, LB, lower bound. Lower bound value is 0. What is the upper bound of your array? It is 4 rather, right? So using this lower bound, upper bound, you can find the middle elements, right? What is the formula for middle element index? LB plus UB by 2, right? So LB is 0, 0 plus 4 by 2 is going to be how much? Is going to be 2, right? So 2 is nothing but 2 is the index of the middle element here. So it means you are going to compare your key with the middle element, right? You don't compare right from the beginning like how you do it in linear search, right? In linear search, what you are doing, you are comparing your key right from the first element of your array until you find. But here, instead of going that way, you will be first finding the middle element, right? So how do you find the middle element? You need to find the index of the middle element. So you will be using this formula, right? Mid equal to LB plus UB by 2. Lower bound plus upper bound by 2. Here, lower bound is nothing but the index of the first element. Upper bound is nothing but the last, element index. So you'll be first taking the average of these first and last will give you the middle element index. So taking this middle element index, okay, you will be finding the middle element. Now you are going to compare your key with the middle element. 30 equal to 30 here anyway found, so you just say element is found and then you come back, right? You will break the loop. But let us say, for example, if you are searching for 20, what happens? When you are searching for 20, okay, you will compare your key, that is 20, with the middle element, but it is not found. When it is not found, you will be comparing whether it is less or greater. Now you can see key is lesser than the middle element. If key is lesser than the middle element, it can be found only in the left half of the array, okay? Because the entire array is put in the ascending order of the elements. So if let us say your key is found to be less than the middle element, obviously it can be found only in the left half of the array. So I can take this as my array, okay? My logical array is going to be this one. So I need not to now search in the right half of the array, right? Anyway, I will not be able to find in the right half of the array, because in right half of the array, definitely the elements will be more than my key rather, right? As we know that the elements are in ascending order. So I will be rescuing from comparing this right half of the array. then I'll be taking only the left half of the array. In that case, what happens? My array size will be reduced to half, right? My array size will be reduced to half, right? Again, I'll be finding the middle element out of it. When I go to the left half of the array, my upper bound becomes what? Mid minus 1. Mid is nothing but 2, so upper bound will be mid minus 1. This is how the algorithm is devised here, rather, right? So you can see here, you have the mid element. How do you find mid? Mid equal to LB plus UB by 2, right? Okay, you will be comparing your key, okay, with the middle element. Fine. If key equal to A of mid, that is the first case, best case, then here you have a flag variable, okay, which is initially 0, now been changed to what? 1, and you will break the loop because you have to do the further searches when you found it, rather, right? Okay. But if this key is else if, okay, key is found to be, let us say, less than A of mid, that is the second case, right? In that case, where your key can be found? Only in the left half of the array. So when you move to the left half of the array, lower bound will be same, but upper bound will be changed. Upper bound will be changed to what? Mid minus 1. Okay, so upper bound will be changed to mid minus 1. Else if, it means the third case, right? If the key is found to be greater than the middle element. For example, your key, let us say, is let us say 45 or 40, whatever, right? In that case, it can be found only in the right half of the array. In that case, UB will be same, but lower bound will be changed. Lower bound becomes what? Mid plus 1. Because you need to take only the right half of the array. So I'll be combining all the cases here in this algorithm while designing it, rather, right? So else if here you can see if the key is found to be greater than A of mid, lower bound will be changed to mid plus 1. Okay. Then you have to repeat this logic. Fine. You will be having this entire thing in do while or while loop, rather, right? So how long you will be repeating this? Until it is found, right? Until the elements are available in the array. When can you say there are elements still available in array to be compared with the key? Only when the lower bound is less than or equal to upper bound. Okay, lower bound should always be less than. If it is equal, that means that there is only one element left. Fine. If lower bound is greater, then what do you mean by it? Array does not exist, rather, right? So until array exists, you will have to compare the elements. This is how the algorithm is made now. The rest of the elements I am declaring here, LB, UB, and your array of, let us say, whatever the size could be, 5 I have taken. Mid, another variable which you need. Okay. First you read the array. You will say that read the array, that is A, and then array, after reading the array, you will be reading the key also, right? Since this is algorithm, I am not bothered about the syntax, so I have declared all the variables required, LB, UB, mid, array, flag, and I log. Then I am reading array and key. This is my logic, okay? So in this logic, what I am doing, you can see, I am first finding out the middle element index. How do I find the middle element index? By, taking the average of lower bound and our upper bound. So what will be lower bound initially? Initially, the lower bound is 0. And for this particular array, upper bound will be what? 4, yes or no? Because the array size is 5, no? So what could be the last element index? Obviously 4. So I am initializing the lower bound and upper bound for this particular array. Before I go for the logic here, I'll be first finding out, once I enter into the logic, the middle element index, right? How do I find? By taking the average of lower bound and upper bound. Then my key is going to be compared with the middle element. Okay. If the key is found to be equal, then I say, flag is 1 and then break the loop. and come out of the loop and say that the element is found. Otherwise, I'll have to compare whether my key is less than or greater than. If it is less than, then I have to move into the left half of the array. For that, the upper bound has to be changed. It has to be changed to mid -1. If key is found to be greater than a of mid, then I have to go to the right half of the array. For that, lower bound has to be changed to mid +1, right? And this logic has to be repeated for how long? Until there are elements available in the array. When array, does not exist, when do you know that array does not? When lower bound is greater than upper bound. So in that case, you will come out of this loop and then check the flag value here. So if the flag value equal to 1, you say that the element is found. Yes or no? You say print key found, right? At which position? Mid position. Yes or no? Else, what do you say? Key not found. Yes or no? Key not found. So this is what the NNP algorithm. Fine. So this is the binary search algorithm. So in this algorithm, the amount of time that does it take for the worst case scenario is the log n, which reduces drastically our comparisons. If you have about 1 million elements, like even worst case scenario as well, it takes only 20 comparison, not more than that. So this is the advantage of log n. In many of the searching techniques in your Google dictionaries, hashing and all, this particular searching technique is being used. Right? This is one of the powerful searching technique which is being used across all the applications, right, of computer. Right. We will now look at the program. I hope this is clear to all of you. I'll first save the previous program here. This is the save option. If I create new project, automatically it will tell me to save. Otherwise, I'll save here. This program is linear search, right? So linear search .c. Now I want to create another project. So when you open the online GDB, you can find left side there is a browser wherein you can find create new project option. So if you create new project, it will again open a window like this kind. To increase the size, I am taking the whole size here. Fine. Now let us write the program. I am writing the program here. What are the variables I require? I require one array. Let us say the size is 5. Flag is another variable which is initialized before 0, and I need a variable I to read the array, and I need lower bound, and I need upper bound variable, I need mid variable. Okay, so these are all what I basically need. Now let us first initialize the lower bound upper bound values. Lower bound equal to 0 and upper bound equal to 4 here as per the size. Okay, then I will have to start the logic here. Before that, I need to first read the array. Fine, I need to read the array. I'll be reading the array here, and the key as well. I need to read both array and key. Enter the array of how many elements? Array of 5 elements. Okay. So to read an array, we need a for loop here. I equal to 0, I less than 5, I plus plus. So you'll be reading here using scanf. Fine. Since it is integer array, we have to give percentage d as a form specifier, and after double quote comma the variable into which we want to read, which is with ampersand at its operator ampersand a of I, we should say, and now we have to read the key, right? So enter the key here, enter the key, I say, key element, only one, so I'll say S to be removed here. And then I'll be reading the key here, percentage T, comma ampersand key. Okay, fine. So as per the algorithm, first the variable declaration, then you can see here to read the array and key we have in read here. We have initial algorithm. Now the logic starts, right? This is a logic. First, we need to find the index of the middle element using this formula. Then we have to compare key with the middle element. If it is equal, then we have to change the flag value and say break. And if it is found to be less than the middle element, then we need to move into the left half of the array. In order to move to the left half of the array, lower bound will be same. Yes or no? Lower bound will be same, but only upper bound will be changed to mid -1. But if key is found to be greater than the mid, then you have to move into the right half of the array where upper bound will be same, but lower bound will be changed to mid +1. So you can see the algorithm is written like that, and this has to be repeated until there are elements to be compared with key in the array. So when array does not exist, okay, you will be coming out of this particular loop and then comparing the flag value. If flag value is found to be 1, you say key found, otherwise not found, right? So this is how you're going to write here the logic of the same. You have to first find the middle element index, middle equal to LB plus UB by 2. I need to give this in brackets because if I do not give, what happens, as per the precedence rule, only UB by 2 is going to perform and will be added to LB rather, right? So I want this whole to be taken as a unit, then I want to take the division of the same rather. So I need to mention it in parentheses here, right? LB plus UB by 2. First I found the middle element index. Now we are going to compare the key value. If key value is equal to A of mid, right? A of mid here, then you will be saying that flag equal to 1 and quitting the logic because element is found. So you have to do the further searches. But if let us say okay, so okay, so now in do while, another case we have is the else if, right? Else if key is less than A of mid, right? Then what will you say? You have to just change the upper bound value, right? Upper bound should be equal to mid -1, okay? And another condition we have is the else if mid is key is greater than A of mid, right? then you say lower bound should be mid plus 1, okay? Because you have to move to the right half of the array. When you move to the right half of the array, upper bound will be same, but only the lower bound will be changed rather, right? Fine. So this is all done here. Okay. Now, after this, you will have to terminate the do while, right? So the condition which you are going to check here is whether LB is less than or equal to upper bound. Fine. Okay, so this is what our logic is. We are finding the index of the middle element here using this formula. Then we are comparing our key with the middle element. If it is equal, then we say fly equal 1 and break the loop. Otherwise, we want to see whether it is less. If so, then we have to move to the left half of the array, for which the upper bound has to be changed. And let us say if key is found to be greater than AF mid, then we have to move to the right half of the array. For that, lower bound has to be changed, right? So then when you come out of the loop, you need to check, the flag value here. So if flag value is found to be 1, okay, then what will you say? Key found, yes or no? Key found at which position? Mid position, obviously, right? So I am printing that mid position here. Else, I will say that key not found, right? Key not found. Okay. So this is what I have discussed as algorithm, which I have transformed into C program here. Okay. So is it clear to all of you? Okay, now we can probably run this algorithm and see. This is C language. You have to choose the language as C, fine, because you can run multiple language programs using this compiler. You can see in the combo box. You can run Java, Python, C hash, Ruby, Perl, Pascal, R, Fortran, all that. But you have to choose your C because your program is C language program. So you have written the program now. You can probably run the program and then see the result. Okay. There is one error here at key, of course. See, we have not declared key variable. So we need to declare here key variable. Okay. Enter the elements of, enter the array of 5 elements. Here we are, let us say, that what is the condition here? What is the precondition? While you are entering the elements have to be in ascending order. This is the condition based on which only the algorithm works rather, right? I'm giving all the elements of this array in ascending order. 10, 20, 30, 40, 50 I've given. Now it is asking us to find the key. You need to enter the key which is required to be set across a particular array. So here I'm giving, let us look at, I'm taking 40, okay. I'm giving the key element as 40. Yes, key found at the third position it has set, yes or no? And similarly, you can probably run again and give another case of elements. As I have discussed, 3 cases, right? The 40 will work with the third case, right? Moving into the right half of the array. And take here another execution of the same. Now let us go with the best case. If I am giving 30, 30 is available at the mid position itself, right? Key found at second position. I'll run it for now. Left half of the array. 10, 20, 30, 40, and 50. Okay. Now let us say I give 20. It is available at position 1. Good. Now let us execute for worst case, that is unsuccessful case. Okay. So if I have to search for an element which is not at all available in the array, okay, let us say these are my array elements. Now I want to search for something like 25. Is it available? Not available. So it says that key is not found. But then after performing all the comparison, but to the maximum only logarithmic it performs, where it is reducing the number of comparisons. Fine. Since the array size is going to be reduced at every iteration by half, the amount of comparison that it has to perform are going to be reduced drastically, and the time complexity that it determines for us in the logarithm. I hope this is clear to all of you.